Hi, Algebra. Today we're going to factor the difference of squares. You can use the date of 327. This is the note packet that you'll need for today's lesson. Let's start with a review of a perfect square. If you take any number and square it, the result that you get will give you a perfect square. We did examine this back in Unit 3 or 4 when we did square root radicals. So I took the first 15 numbers and I'm going to square them. And these are the values of your perfect squares. It's best if you can commit these to memory. It will make the calculations a little bit easier for you if you just know them off the top of your head, at least 1 through 10. Now, variables can be perfect squares. If you examine their exponent and it's an even number, we're simply going to divide by 2 to split it up equally into two identical factors. So x to the 6th is even. The two identical factors are x to the 3rd times x to the 3rd. Now there's other factors that are possible, but we're trying to keep the factors identical. For x to the 16th, we have x to the 8th times x to the 8th. And x to the 32nd, if we split it equally, it's x to the 16th times x to the 16th. So any even exponent can be split into two identical factors, which will help with our squares. Remember, you can stop the video at any time if you want to try any examples on your own. So when we're factoring our trinomials, this is what the perfect squares format will look like. It'll appear as a binomial. You can see we have a squared, which is even, so it's a perfect square. And b is squared, also a perfect square. What we're missing is the middle term. But the middle term has to add up to 0. So because it does add up to 0, we've eliminated it because all of this is 0. When you have this structure, you're going to see two identical binomials. We're going to have one with addition and one with subtraction. So they're the same except for the signs in between, and that will cause the 0 in the middle. So let's try one. I know that n squared is perfect and 25 is perfect, but we're missing that middle term. If it helps, you can rewrite it with the 0 in the middle. You can make a list of factors for negative 25, but I know since they have to add up to 0, the factors are identical. So one is plus 5 and one is minus 5. Okay, let's try this example. If you want to expand it to include the middle term, you can do that. So the center is going to be 0 times x times y. What you'll want to see is that the first term, 36, and x squared are both perfect squares on their own. So we're going to separate that into two identical factors, and that will start both of my binomials. You'll also notice that 49 is perfect, as well as y squared. So that'll be in the back end of both of the binomials, and the only thing different is one is positive and one is negative. So now this one is completely factored. In example 3, we'll do the same thing. If you want to include the middle term, you can do that. But I notice 169 is a perfect square, so that will be 13. So that will be present in both factors. And then 16 and y squared are both perfect. So one will be plus 4y and one will be minus 4y. Now, we have learned how to remove the greatest common factor as our first factoring technique. So now that they're going to be more complex, this is the first step that you need to do. So examine your binomial or your trinomial and try to remove the greatest common factor first. Once you've removed the greatest common factor, you should have a leftover quantity. It could take many forms. It can be a trinomial, it can be difference of perfect squares, it could be a binomial, or it might not be factorable at all. But then we'll have to continue to factor if it is. So we're going to try this example. I'm first going to look at both quantities and see if they have a greatest common factor. So I can tell 48 and 12 have 12 in common, and they both have at least one A that can be given up as a greatest common factor. Now, I'm going to go through and divide both terms by 12A. So there's the GCF, and these are the leftover terms. This binomial, though, you have to check. 4 and A squared are perfect squares, and 1 is a perfect square. So we're going to separate this again. So 4A squared will become 2A. Those are the first quantities. And 1 becomes plus 1 and minus 1, and now it's completely factored. So let's try here. Is there a greatest common factor? And we want to remove both numeric values and variables if we can. So I can see that they both have a 2 and they both have x to the third power. We're going to divide both of these terms and see what's left over. My remaining factor is a binomial, but again, I notice x squared is a perfect square and 49 is a perfect square. So we're going to further factor. We're going to keep our GCF, but now this remaining binomial turns into x minus 7 and x plus 7. How about number 6? Is there a greatest common factor? It doesn't appear that it has anything in common, both numeric or variable. I can see that 4t squared is a perfect square, but I know that 27 is not. So this is not the difference of squares. At this point, it doesn't look like this one can be factored at all, so this example is not factorable. You can write it as 1 times the quantity of 4t squared minus 27, or you can simply state that it's not factorable. Okay, number 7. Always start with the greatest common factor. So I'm going to remove 2. That leaves behind x to the fourth minus 81. Both of these terms in this binomial are perfect. So we're going to break x to the fourth into 2 identical factors and 81 into 2 identical factors. Are we done? If you look here, x squared and 9, those are both perfect squares as well here. The only difference is when you factor the first term here, the first binomial is a difference, the second term is not. So this x squared minus 9 will break down again into x plus 3 and x minus 3. This problem has 4 prime factors, and we must list all of them. Number 8, first remove the greatest common factor and then go through and divide and see what's left over. In my remaining binomial, both of these are perfect squares, so I will separate them into identical quantities. One is positive, one is negative. Now this one has 2 variables. We're still going to start with the greatest common factor. So what's shared between 20 and 45? And then if I look at the variables, they both have x's, but they can only give up one x. So I'm going to pull 5x as a GCF, leaving this binomial behind. In both cases here, both of these terms are perfect squares, so we're going to separate them into identical quantities, 2x plus 3y and 2x minus 3y. And that's as far as that one will go. For number 10, is there a greatest common factor? Let's remove it. 7x is shared, leaving behind x minus 11. At this point, this binomial is not factorable anymore, and the process will stop here. This goes back to learning how to factor trinomials. There is no GCF. What I'm going to do is make a list of factors that will multiply to negative 21 and add up to 7. Remember, the sign is important. One of the signs has to be negative. When I look at these factors, I do not find a set that adds up to 7. So at this point, I have to conclude that this one is not factorable. For number 12, pull out the GCF. And we want to write down what is left behind. This trinomial we're going to go ahead and make lists of factors that multiply to negative 42 and that also add up to 1. If you think you can do this factoring without a list, you're welcome to try it. Make sure you have the correct signs. One is negative, one is positive. So as I make the list, I'm looking for the set that adds up to 1, and it looks like negative 6 and positive 7. I'm going to include the GCF when I finish the factoring process. So there's x minus 6, x plus 7, and my GCF of 2. Make sure all factors are there. Number 13, pull the greatest common factor. What I'm looking at in this binomial are 2 perfect squares, which means I can break them down into 2 identical factors. So we have x plus 5 and x minus 5. For number 14, we're going to pull the greatest common factor, leaving behind a trinomial. And again, with numbers, the product of 72, I'll probably have quite a list of factors. So here's my list. We're looking for the set that will add up to 18. And it looks like 6 and 12 will be the set we want. When we write our final answer, we'll have our GCF of 4, and then we have D plus 6 and D plus 12. This will be the homework that you want to complete this lesson. It's homework number 96. If you have any questions going through the homework, please feel free to call me or text me or send me an email. Have a great day.